Thank you very much for the brief introduction. And yeah, I'm happy that you could make it possible for me to join online, because it was not possible for me to be there personally. So thank you to the team who made it possible. Yes, and I quickly also want to start with this presentation on CO2 reduction in sprayed concrete tunneling. So I would say let's just dive right in. I will try to minimize this and let's go. So in 2019, humans have produced 148 tons of cement, and with this emitted 95 tons of CO2 every second. As you can imagine, with every second is like 95, 190, 285. This is like bam, bam, bam. And you will see that this is likely a true challenge for the whole industry. And this is the topic today. And I would like to take you by the hand, and Wolfgang, my colleague, as tunneling expert, us together, we would like to dig a bit deeper into the topic and explain how we can tackle that challenge and what we have in our hands to do. So let's take a quick look at the agenda of today's workshop. So I will quickly go with you through the impact of the cement industry and put it into a context to the global climate crisis. And afterwards, my colleague Wolfgang will dig a bit deeper together with you into CO2 reduction in concrete and especially shotcrete formulations. He will speak about life cycle assessments of new tunneling construction, innovative planning approaches, and sustainable building materials. And he will briefly give an introduction into composite shell linings and what we can do with it. So starting with the question why sustainability even concerns the construction sector. Here you see quite some facts. So the construction sector consumes 36% of the world's energy. It is also responsible for 39% of all global greenhouse gas emissions that are polluting our atmosphere, and it causes 10% of the world's particulate matter emissions. This is quite a huge impact that we as a construction sector have on our planet, and we have to take the responsibility of pushing it to a more sustainable way. Also, the construction sector is contributing to the displacement of productive land, biodiversity loss, and just to have the last box down here below in the right corner. After water, concrete is the most used material in the world, with almost 2 cubic meters per person and year. So on a head count, this is quite a lot. And just to tell you guys how much this is. So if we would pour all of this globally consumed concrete into a pillar with an area of just 1 square meter, we would end up with a structure that would go 30 times to the moon. So just to have these masses visualized in your heads, I think you see that these amounts are quite significant. But looking a bit into the first, or one of the first numbers I showed, so 39% of the global greenhouse gas emissions can be related back to the construction sector. And you can look at it a little bit more in detail if you have a look at the diagram on the right-hand side. So the annual global CO2 emissions are showcased here. And you have, of course, other industries, you have transport emissions, you have others. And just from the building sector, you have these 39%, which also divide into 28% being from building operations and 11% from the construction itself of the structure and the building materials that are used. And speaking of building materials, this is what we want to talk about today. And that's why we want to have a look at the concrete itself. So on this diagram, you see the global cement and concrete production in billions of cubic meter or tons in case of cement. And you just see, just in the last couple of decades, how strongly the demand for concrete and cement has been increasing. Looking at 1980 with concrete production of 2.8 billion cubic meters and forecasting to 2030, we have a factor of 5.4 just within these few decades. And in 2030, we will be at 15.2 billion cubic meters, which is, yeah, quite a lot. But to know how these masses affect our environment, we have to look we have to look a bit deeper into the essential components of a concrete. So this is why I want to show you this little picture here that I prepared. So this is basically a cubic meter of concrete, and we have the contents. So basically 8 to 15% of cement are in there, which is of course for a like very normal ready mix, our type of concrete. We have 2 to 7% of water. We have our chemical admixtures, which are dosaged quite low. Then we have our aggregates, of course, and the additives. And just to quickly remind everybody of why we need these components in our system. So because it's a 5-component system, most of the times we have the strength development, which is basically we need the cement and the water for it, for the hydration part, for the chemical reaction. Then we have our fillers with the aggregates and the additives, and we have the admixtures and the additives, which both are used to manipulate the fresh and hardened concrete properties. So all of these components are needed to create a concrete. And if we have a look, not only just remembering cement being the mass of 8 to 15%, but looking at the CO2 emissions that result from these components in the concrete, cement is responsible for over 90% of all CO2 emissions that are basically stored in or resulting from a cubic meter of concrete. Water just below 1%, chemical admixtures as well, additives and aggregates being responsible for around 8% of the CO2 emissions. But yes, you can see here, so cement is really the thing we should be looking at, which is why we're doing it now. And just the basics, basically. And before we do that, I quickly want to give you an example just to put everything into perspective or relation. So having this example here, we have 1 cubic meter of concrete, which basically contains 290 kg of cement in a normal ready mix type concrete. Then we can check, okay, with the CEM2A, for example, we would have a carbon footprint of 220 kg of CO2. Adding up everything else that goes into it, so being 90% originating from cement, we have a footprint for this 1 cubic meter of concrete of 240 kg, and adding the reinforcement will be at 290 kg of CO2. And just to put it into relation, we could drive a car almost 2,600 kilometers to have the same footprint. So you could either build 1 cubic meter of concrete or use 1 cubic meter of concrete or drive 2,600 kilometers by car. But we have to look at the CO2 emissions and where they originate from, because cement is not cement. The main problem here is the clinker in the cement, so the clinker production process itself. And that's why I brought you this picture of the process, just a very basic basic description here. So you have the raw material flow, you have the quarry from the site, then you crush the limestone, then you mix it, you dry it, you ground it. This is all taking place here. Then you have your fuels that you use to heat up the rotary kiln. And this is really where it gets interesting, because the rotary kiln is the part where we have the highest emission within the production process, which you see on the right-hand side. So the fuel emissions, just to heat everything up, to have the energy and the heat production, this is responsible for 35% of all the production process emission. And then you have the process emissions, which are basically going back to the chemical reaction. So this is basically the responsibility of the chemical reaction from limestone to clinker. And all the others, so power emissions, including grinding and transports, are really low in comparison to this part of the process. That is why I want to dig a bit deeper and give you just really the basics and remind you guys. Probably many of you know this already, but let's have a look again. So you have the rotary kiln here in a little bit more detail. You have the raw material flow from left to right, and in the end you end up with cement clinker. You have the fuel combustion to get the heat into the system, and to have the decarbonation process, and the gas flow is originating here, you can see it, and you end up with CO2 emissions per ton of cement clinker of up to 900 kg. And why is that? Here you see in the next slide that basically within this process of the rotary kiln, 50 to 60% of the CO2 is process related, and 40 to 50% is originated from the fuels that you use to heat up the system. And the chemical reaction behind this, you can see it up here in pink. So basically the calcium carbonate limestone basically is heated up to 1550 degrees to have the chemical reaction, the decarbonation of the limestone to calcium oxide, which is also better known as quicklime, and CO2. So for every molecule of calcium oxide you also have one molecule of CO2. And this is basically something that you cannot avoid. So if you want to have clinker as a binder, which is I would say the best binder we have or we know, then you cannot get rid of these emissions. These are just there. And what does this mean in numbers? So basically we consume 4.65 billion tons of cement per year. We as people living on this planet, we emit 3 billion tons of CO2, and that makes around 8% of global anthropogenic, so human-made CO2 emissions. And as you can see, this could be a massive problem. But on my next slide, I would like to show you a little bit more into context. So where do the CO2 emissions come from per region? And what does it mean historical wise? Because many of you could be saying, and I was thinking about this too, like, okay, yes, I know we have a footprint, but it's just us in Europe, and we play a minor part compared to giants like China or the United States. And yes, that is true. But I would like to remind everybody of our responsibility that we have historical wise. So this is why you see on this slide the cumulative CO2 emissions per region starting from 1750. So 1750, maybe a fun fact, Mozart and Marie Antoinette were born in the 1750s. So it's quite a while ago. And you can see that in that time, all the CO2 emissions that were produced up till then were originating from the UK, basically. So Europe, but basically it was the UK. And in the 1950s, which is the red dotted line here, you see that 50% of these emissions, because of a huge increase of CO2 emissions by the United States, so 50% were still, could be located to the European continent. And at that time, you see that also China is tremendously producing CO2 and is really picking it up and having its impact on the world's CO2 emissions. And up till now, so this is a data from 2019, still we have an overall, so from all the CO2 emissions that were produced until this date, of 32%, the United States emitted around 25%, and China is at 13%. Of course, if China is keep continuing what they're doing and the rest of Asia, we will have a tremendous problem. But this slide should simply show that we should not forget our historic responsibility, which is probably why we should be the first movers. I also want to point out the connection between prosperity and CO2 emissions. So on this slide, you see the annual consumption-based CO2 emissions per capita. And on the axis below, you have our gross domestic product in international dollars per capita. And what you can see here is that there is a strong link between prosperity and CO2 emissions. So in the left corner down below, you have all the very poor countries such as Mozambique, Ethiopia. So basically our African continent, people that live there and the states that are originated there. And of course, states as India or China, China a bit more located in the middle, and all the very wealthy countries on the right-hand side. So you can see that there is a strong link between wealth and CO2 emissions, and I want to point that out in one example. So if you look at the bubble from India, this is of course a huge bubble because they're just pretty much Indians on this planet. And the second one I want to point out is Germany, for example. So if you look at India, the bubble being quite big, so they have a tremendous impact on our CO2 emissions in the world, but they are only using 1.92 tons of CO2 per capita, whilst our German fellows are using or are responsible or have a demand for 10.37 tons of CO2 per capita. And you see also the difference in the gross domestic product, which is quite immense. And I mean, talking about Luxembourg, these are just very few people, but they are really taking the biscuit. And with the rising prosperity all over the world, the demand for concrete also increases because we have the link also between prosperity and construction or use for buildings, more infrastructure. And I mean, who could deny that this is something we all need and want to also have a working environment, civil engineering structures, which you can imagine, these are widely linked to the wealth of a country, having good infrastructure and so on, especially regarding tunneling systems. And this is a slide I want to show you to check out the cement demand over the time here showcased. And you can see in the gray area, this is basically us, the industrial nations, Europe, the US, and so on. And you see that our demand is slightly increasing, but not really, and it will be steady. The demand for cement in China will slightly decrease or decline, whilst India and other developing countries will rather have a higher need, due to the rising prosperity. So, not forgetting our responsibility historical-wise, we have to act. And we have to act now, and we are basically looking at it now, how we can do it. So sustainable development, I brought you a definition of it. Sustainable development refers to a development that serves the need of the present generation without jeopardizing the ability of future generations to meet their needs. And this is something that also the cement industry knows, which is why they target 24% CO2 reduction within the industry to meet this 2 degrees Celsius global warming limitation that was set in the Parisian Agreement. And this looks a bit confusing here, but I want to quickly show you and explain this diagram. So on the left side, you have the direct CO2 emissions per year in milliarden tonnen, and you have the time down below. And if you look at the scenario, the reference technology, like I said, our demand will increase for cement, which is why if we do nothing, which is the scenario in the black line, our emissions will increase, just from the cement industry point of view. And if we want to meet this global warming limitation of 2 degrees Celsius, this means we would have to reduce this 24% relating to the 2020 value. And now we have to fill the gap. So how can we do this? And the cement industry had a definition of quite some scenarios. So we can still improve the energy efficiency, but it's not so high of an impact because they are already doing this also from a money perspective already. Then we could be using alternative fuels, which would be 12%. So okay, also not that huge of an impact. We could reduce the clinker in cement, so using more clinker efficient cements, using higher amounts of supplementary cementitious materials. And the very, very big part that is also pretty well known now is new technologies, and they are really building on this carbon capture, which we will need, and so whether it be carbon capture and storage or utilization. And you will see that this will have to come tremendously from the year of 2035 to reach this goal, this very ambitious goal. So basically we could sum this up that we have 5 levers to improve the life cycle assessment or the footprint of a concrete, which is green energy, it's a substitute of clinker, it's optimized concrete mixes, and it's compensation. So which is basically the carbon capture storage story. And then, of course, we have other things that we should keep in mind, such as using recycled concrete and capturing CO2 within the material, because this is also a very good way to limit resource depletion. And I think with this slide, I want to show you that we ourselves have to prepare for a pretty different cement world in the future, because our cements are becoming more complex and diverse. Just looking at this in 2014, we have pretty much a composition of our cement and usage in concrete of 65% clinker, 13% blast furnace slag, we have fly ash, we have limestone, and some natural pozzolana, but not too much gypsum. And this will change a lot. So the cement world will get a little bit more colorful. And this you can see here on the right-hand side with the scenario of 2050, the 2 degrees goal. We will have less blast furnace slag. We will have almost no fly ash anymore due to changing processes within the steel industry. We have a lot more limestone, which is an inert material, so it's not taking part at any hydration processes. We will have a natural pozzolana again, but especially our focus in the world, so this is a global thing, will be more on calcinated clay as well. So we will have to adapt, and we will see how this works out. But these composite concretes are also very interesting for more greener concretes. And we want to look here at this very basic diagram where you see the CO2 in kg per cubic meter. And you have here the different type of cements or concretes that are made with different type of cements. And you see that standard concrete with a CEM 1 reaches from around 270 kg of CO2 up to almost 390, whilst a composite cement with SEM2A, for example, or SEM2B even, will be already a bit lower, and you have a broader range of pushing this CO2 content for a cubic meter of concrete. But where we really have the leverage is when we are using CO2 optimized concretes, or also called these green concretes, sometimes called like that. And we have a CO2 reduction possibility of up to 30%. To really push the CO2 embodied carbon of a cubic meter quite below 200 kg. And now you can say, all right, yes, this is all sounds very nice and sounds very fine, but we of course have some implementation obstacles. So they would say, this is not permissible. It's regarding the standards, we couldn't do that. We would have to get an approval, and it's not really required yet. So why should we bother at all? Probably it's not going to work on site as well, or we have super high costs. And I like the question of this guy here. Like, how do we actually evaluate if a concrete is sustainable at all or not? Who knows how to calculate something like that? And yes, it is true. We have some milestones that we have to tackle for overcoming the implementation obstacles. And here I want to quickly show you the main three that I see. So basically, we will have to adapt the standards and the approval processes. I'm not sure if you are familiar, but in Germany, approval processes can quite be a pain in the ass. And we would have to make sure that low clinker composite cements are being used in large areas below minimum cement values. And also not only relying on the experience to know if a concrete will work in this or that structure, but rather relying on the performance and the durability, which is looked at in advance, and the CO2 footprint. Of course, we will also get international policy instruments for the construction sector, which are already been worked on with the EU taxonomy, for example. And we will have to look at all phases of the life cycle for construction projects, and also the building materials in CO2 context. And probably we will also get a CO2 factor in tenders for major projects. I could pretty much imagine something like that coming soon. What I want to point out as well is that I think CO2 reduction should be an integral part of the business model. So not only worrying about costs or anything, because I think the profitability of a company can really rise when they extend their portfolio to CO2 optimized and high quality concretes, and just to avoid low quality concretes in large quantities. This in the future will be key. And of course, the most important one probably being to be aware of the different options that we have and the solutions that are already there and could be leveraged at all parts of the value chain. And this is why I think Wolfgang and I are here today, to just put a bit more awareness on this topic. And Wolfgang also asked me to quickly give an introduction on how to know the CO2 footprint of a product, for example, and life cycle assessment. What is it, and how do you rate sustainability? So basically the question of this guy, how do we evaluate sustainability? And he asked me to point out what an EPD is, because probably not everybody knows. So an EPD is the abbreviation for an environmental product declaration, which is a document that contains all different kinds of environmental impact data on the building material or the building product. So we have basically a lot of different impact categories. I think probably the most widely known is the global warming potential. But there's also, for example, the resource depletion, its acidification, and many more, which are then assessed and basically hold on to in this kind of document. And an EPD is always quantitative, it's objective, and it's externally or third-party verified, which makes it also comparable in many cases. So what I really want to point out here is that the fact that if you see an environmental product declaration, or if you have one for a product, it does not necessarily mean that this product is sustainable or more sustainable than another one. It basically means that you are being transparent about it. So keep in mind, not if the people show you an EPD, this does not mean that the product is more sustainable. It's just really, showcasing the footprint. And speaking of footprint, I want to quickly talk about design phase, especially in tunneling. So we are already today in tunneling. We are looking at the geological prognosis or the geotechnical prognosis, and we're looking at time and costs, and we're calculating these over the Big Bang, I would say. So why aren't we looking at sustainability as well? I think this could be a huge part to getting our goals, to reaching our goals. And I quickly want to point out that the timing of the implementation of the sustainability criteria is decisive for the success and the costs of a project, which is why I showcased this down below. So you have these different kind of phases here. You have the design phase, you have the construction and the operation and maintenance. And you can see that in the design phase, when you implement sustainability criteria here, you have quite low costs and you have a lot of options. Rather, if you go into the operation and maintenance phase and try to implement or benefit in any way, do something about the sustainability of a structure, for example, in tunneling, you will not have a lot of options to do so, and the costs will be quite high. So keep in mind, if you want to do something about sustainability and if this should be a part of the project, you have to start early. And promise, this is my last slide, and then we will get fully deep dive into tunneling construction with my colleague Wolfgang. Here you see basically the phases of a construction of a tunneling project or any kind of project, basically. And we added the design phase because we think this is quite important. And what I want to point out is that you have initial costs and initial carbon. And you have follow-up costs and follow-up carbon, which would be these. So you have the design and construction phase linked, and then you have the use, maintain, and reuse phase. And I don't want to explain the whole slide, but I just quickly want to showcase the design phase CO2-wise and the emissions that are caused by the phase and the influence of this phase on follow-up costs and emissions. So here you see basically the total CO2 emissions caused by the phase itself. And if you look at the design phase, these CO2 emissions will be very low because it's basically desk work. You have to define, you have to put it into the contract, you have to make simulations. And so the CO2 emissions are quite low. But if you look at the influence on later CO2 emissions of the construction itself, then the influence is very, very high because you have these many options and you have to really, define the further process and choose the perfect and more sustainable way of constructing, using and maintaining the structure. And with that said, I would like to hand over to Wolfgang, who will showcase you in some way how we could do that.